Welcome everyone to the next lecture on accelerated data analytics. In the last lecture, we went through some of the motivation of using accelerated data analytics. We went through the description of the job profiles for a data engineer, data scientist. What is the cycle? What are the activities that they do? We looked at the different stacks traditionally used. So what we are going to do today is we are going to quickly go through some of the modules of Rapids, and we will show you a demo of how to write the code. So let's get started. Maybe a quick recap of the software stack of open source data science platform. We talked about the most popular ones being used on the CPU side of it. Pandas primarily used for analytics. Scikit-learn or sklearn being used for machine learning algorithms. And then we have other libraries or modules for NetworkX, which is primarily for graph analytics, deep learning, and then matplotlib for visualization. And we also talked about Dask. Dask basically helps us in making our computation go distributed. So basically the responsibility is towards that side. So we also talked about the equivalent rapid stack, which is the accelerated GPU science stack. If you see, we are replacing the bottommost layer with the help of use of Apache Arrow, so that everything remains in memory in the GPU. And the other advantages that we saw last time, also removing the marshalling and unmarshalling, serialization and deserialization across different modules and all. Today, we are going to concentrate on cuDF and cuIO, which is a replacement of Pandas equivalent. It is like Pandas equivalent, and we'll be going through a demo of how you could utilize cuDF and cuIO. If possible, if time permits, we'll also go through cuML, show you a demo of also what machine learning algorithms exist and how we can utilize them using cuML, which is cuDA-ML. And tomorrow we are going to go more into the Dask point of view. So let's get started with cuDF. If you remember last time, we said how the acronym cu comes into the picture. Cu basically stands for CUDA, which is the GPU architecture, Compute Unified Device Architecture, and DF is the data frame. So we are basically talking about having data frames which are accelerated on the GPU using CUDA. So from a point of view of the ETL technology stack, which is the extract, transform, load part of it, this is how the overall wrappers are generally written inside Rapids. First of all, as you can see here, the bottommost layer is our architecture of GPU, which is CUDA, Compute Unified Device Architecture. Above that, we have certain libraries which are part of the CUDA ecosystem. Like Thrust is a library which is like C++ STL equivalent, which is standard template library equivalent in GPUs. We have other kinds of libraries also which exist in the CUDA ecosystem, which are primarily C++ or C based. Over that, we have the Rapids ecosystem basically has developed a layer of cuDF functionality which is written in C++. So all those calls of the libraries of CUDA, which are also in C++, are basically done via this cuDF C++ calls. But for the Python users, basically they end up writing code in Python, and for the binding or for the calling of C++, the internal usage goes via Python. So Python is the one which is used for converting your Python calls to the C++ calls behind the scenes. So the first component in this pipeline, in the ETL pipeline, which is the backbone of the data science, is libcuDF. So as I told you, cuDF, libcuDF is basically a C++ library, and it is primarily meant for creating data frames, which is what nothing but a structured data type, right? Like in form of table, which has rows and columns, right? Um, Behind the scene, for all of the APIs which are provided, there are CUDA kernels or CUDA functions which are running in parallel on the GPU. Like if you call a sorting function, join, group by, reduction, whatever those functions are, they are basically exposed as C++ functions. You can see here, like here, we are calling the gather function. This gather function is the one which will do kind of a reduction operation on the columnar data that you have. So there are various other kinds of functions as well, and there are options to also scale them across multiple GPUs. So as I told you, there is a libcuDF is basically a C++ library which primarily calls behind the scene CUDA libraries like Trust and all, while cuDF is basically a Python wrapper over all of this. It's a Python library for manipulating GPU data frames, and it is primarily meant to look very similar to Pandas API. So the idea is that if a user has already a sequential code using Pandas, it becomes very easy for them to just shift to this module and import cuDF instead of importing Pandas, and rest all APIs should ideally look the same. It also has APIs where you can import the data from Pandas or convert your GPU cuDF based data frame to Pandas equivalent. And behind the scene, it calls the CUDA C++ library, which we just saw some time back. And we can also define, suppose, as I told you, that many of these functionalities should ideally run on the GPU, and there are C++ functions which are written behind the scenes already for join, for string operations and all. But what if you want a function which is kind of not present in the standard list, right? What if you want a user defined function which does not exist and you want to do that on your kernel database? So cuDF basically provides JIT compilation, just-in-time compilation of user-defined function using another package called as Numba. In fact, we will be looking at how to use this to write your own accelerated functions to be run on the GPUs. So this is one of the thing where you need to slightly understand some of the CUDA related details into more to understand the architecture, and we will be looking at it in a certain while when we start looking at the demo. So it has various functions, including string support as well. It provides a lot of regular expressions. You could do element-wise operation, group by operations, and there are various. So as we had told last time, that Rapids is basically an open source project, and everybody, it's a large project. There are so many modules and packages inside it, so many contributors from around the world, and it keeps on improving. By the time you might start using it in your own project, you might see more functionalities which we are seeing is futuristic might have already been added to the Rapids ecosystem. There is another package which is very key for faster data loading, which is called as cuIO. cuIO is basically an API which provides you functionalities for reading files or doing IO operations, like reading a CSV file. There are different kinds of readers, like ORC reader. If you're having a JSON file, then read a JSON file. And behind the scene, it supports a very high speed read functionality and lower latency using certain features like GPU direct storage. It basically bypasses a large amount of bottlenecks which are there behind the scenes when you read from a file and directly store it in the GPU, and that's why it's called a GPU direct storage. So it will take care of all the optimizations whenever you want to read large files onto the GPU. So it does a lot of operations like parsing, because like JSON you need to parse. It does the parsing and decompresses wherever possible. And cuIO is one of the most critical component in case you are reading from files as well. So with that, let me quickly move ahead and move towards the demo part of it. So behind the scenes, what I have done is I am basically running a particular lab. And just to again show you, previously we had shown this to you that I have basically created a Docker container, and we have provided you some of the links on the Slack channel, but along with that, I'm going to also provide the links again once more at the end of the lecture on the Slack channel, where you can find this source code that we are showing. And if you want, you can also run it on the cloud infrastructures, which are free versions, or if you have a GPU access, you can use the container to run it on your own machine as well. So you can see here, I'm running a Docker container. I'm exposing it to all of the GPUs, and behind the scenes, I'm actually running on a particular port. So you can see here, I've already launched the lab, and just to show you, the lab is running on the machine. And this machine basically has primarily 3 cards, GPU cards. It's a slightly different card. This is Quadro GV100. You can see here Quadro GV100. This is a Volta card. This one, as you can see, has so much of memory, 32 GB of memory, which is present in this Volta card. It is a desktop actually, not a server. So it is having an active cooling component with its own fan and all, and it is sitting in a workstation at my desk at this point of time. So as you can see here via NVIDIA SMI, I can see that I have the GPUs exposed to me inside the container. So the lab that I'm showing you here is basically a lab which has different components of Rapids, and we are going to go through each one of them. So the lab, basically whatever I showed you in terms of Rapids ecosystem is kind of present in the theory section, and what I'm going to show you now is the part of cuDF. So the component that we are looking at here is cuDF, and as I told you, basically, so I'm going to keep on running some of those things. So some of you should be already familiar with the CPU equivalent, which is pandas. Generally, you will have 2 types of data, unstructured and structured. When I say unstructured, I am generally referring to data like text, images, or videos. When I talk about structured data, I am generally talking about columnar structures like in form of CSVs and all. There are various tools which exist in the Python environment to do a lot of things, but one of the most popular one out there is pandas, which represents data in form of a table. And it allows you to manipulate the data and perform various kinds of operations that we are going to see in this particular lab. So the first thing that I'm doing here is I'm importing pandas, and after importing the pandas, you can see here what I'm doing is I'm creating a data frame. In the data frame, what we are doing is I am creating certain key value pair. So you can see here DF of key and DF or value, and then I am printing values. You can see here it has created these values 00223 as the key, and the value is form of a range from starting from 10, which is in type of float, you can see, and it goes till 10, 11, 12, 13, 14. Right? So this is how very easily you can actually create a data frame, and then you can perform different kinds of operation on this particular data. So here, like one of the example is that what I'm doing is I'm telling that I want summation of all the columns of value, and then print the finally aggregated value. right? So you can see here, if you just add up these values from 10, 11, 12, 13, 14, the value which will come is 60. So what you're doing is you're trying to do operations on this data, certain kind of operations on this data. Now, Pandas, as you can see, is very flexible and it is quite good. But when we talk about working on smaller data set, it works really, really fine, and it can give you all the benefits that you have. But if you're talking about increasingly complex workloads where you want to do more complex functionalities on it, and or if you have a large data set that you need to work on this data frames on, in that case, we recommend you to go towards Rapids, which is the equivalent of the pandas. So you can see here what we are doing is we have imported cuDF. Instead of importing pandas, we have imported cuDF, and rest all values remain the same. You can see here that we have cuDF data frame, we have key and value. There is literally no change apart from the fact that instead of importing pandas, I have now imported cuDF, and rest all things remain the same, except for the fact that these values are getting created on the GPU. And when I run any of the activity on this particular data frame, like summation here, it is actually going to run this on the GPU and not on the CPU. So this is the only change, which means you start using the GPU functionality on by using the data frame cuDF instead of using pandas. So now we are going to look at different kinds of functionalities which are provided on the pandas, on the cuDF part of it, and it is based on the guide of 10 minutes to cuDF, and we can see some of the activities which will give you an idea. In the end, we'll end up with showing you when can you actually get the benefit of cuDF. Ending with that in this particular notebook, followed by writing your custom defined functions. So you can see here, we are actually creating an object instead of creating a normal one. We are creating a series, and you can see here in this particular series, you have certain objects which are also null. So you can also specify values for each column. Now you can see here, you are creating a data frame which is of size 20, and you can see here the A column basically has the range till 20, while B is actually a reverse range and C is again the normal range here. So when you print the value of DF, you can see here you have basically three columns, A, B, and C. A and C being a normal range, B being starting a reverse range. And you can see here the value starts from 0 and goes till 19. And for the PDF also, so this is another version which I just told you that cuDF is kind of compatible with pandas, which means you can actually create a pandas data frame. You can see here I'm creating a pandas data frame, which actually means this is going to create the data frame on the CPU and not on the GPU. And then I say data cuDF.data frame from pandas. So which means I am importing the data which was created on the CPU to the GPU. So it takes the values of data frame created on the CPU using pandas and transfers them behind the scene to the GPU to be used in a cuDF environment to be run on the GPU. So there are different kinds of visualization techniques which are also available. Like this will just print the head values, which are the first two rows primarily. You can also sort the values based on a particular column. Like here we are saying I want to sort the values based on B. And if you remember, B was kind of inverted in nature. So the value started from 19 and it went on till 1. But when I sort the values of B, the values of B are getting sorted, but at the same time its equivalent row values are also getting changed accordingly. So you are doing sort based on this particular value here, right? You can print a single column if you want, like this, or So I just don't need to go to that part. Or what you can do is you can select rows particularly. Like here you are saying, I want rows from index 2 to index 5, right? And the columns that I want those for is A and B, and I don't want it for C particularly. So you can see here, it starts from 2 and it goes on till 5. And we are only getting the data which is of column A and B. So df.loc locate, and then we are giving it the range, the rows and columns that we want to be exported as. We can also select via a particular location using the iLoc function. And you can see here that I want only the location 0. So in that particular case, it is giving me all the 3 values of the columns at the 0th row. So A having 0, C having 0, and the B column having the value 90. So it is giving me the 0th row of all the 3 columns. And you would have guessed it by now. What does this do? So you can see here that it is basically saying I want the rows 0, 1 and 2, and I want it for column 0 and 1. So if you can see here, when I give a range in this particular fashion, it excludes the last part, right? So I'm saying I want 0, 1 and 2. So it is taking from 0, 1 and 2, and this one is also 0 and 1. So it is giving the first 2 columns and the first 3 rows primarily here. Similarly, I think by now you would have guessed it. What does this do? So it will give me the 3rd row and the 4th row for all the columns, which is A, B, and C, because we didn't explicitly state the column part of it, excluding the last one here, right? So this is how it is. And so let me just not give you this exercise. This is kind of very simple. So we will give you much more tougher exercise in a bit, where you would be able to select something. So selection of rows in a data frame or series by direct Boolean indexing. So Boolean indexing is another feature where you have your data frame, and what you're saying is that only if the value of B is greater than 15, then only put it, then only print it, right? So only the values of only the rows where the B value is greater than 15 becomes part of the new frame, right? Or if the BU value is only 3 in that particular case. So if you see here, I'm using a particular API called as query. So we can use the query to get these details. So here I use the conditional statement in form of logic, while here I'm using another API, which is the query, and query basically states that only if the B's value is 3, then only select that particular value. You can also assign certain variables. If you're writing Python codes, you're taking the data from somewhere else. You can do the same thing by using a component inside Python. So at the rate basically refers to a variable which has been previously assigned. So this is all fine.